Speaker is Kenta Cho.
Thank you. So good morning, everyone. So I will talk about semantics for a quantum programming language by operator algebras. By the way, this is my master's thesis work in the University of Tokyo, but I'm in Nigeria. So this is an overview. So I will give a semantics for a language QPL designed by Selinger, Pete Selinger. So I think he is in this room. And so use the category of W star algebras and normal completely positive pre-unitary maps. This category is DCP-oriented symmetric monoidal category with DCPP of bottom and this symmetric monoidal category with DCPP of bottom and its silent product. And this is nice enough to semantics for QPL. So what's this category and what? Okay, this is these maps are seen as quantum operations in the Heisenberg picture. And so in the first half of this talk, I would like to explain this point. Okay, so this is outline. I will start with quantum operation. So this notion is established by Kraus. So consider Hilbert spaces H1, H2, and let T of H, the set of phrase class operators. Then quantum operation is a linear map between the sets of phrase class operators that is completely positive and Fresnel equation. So why is it quantum operation? So consider state or density operator of H1 that is positive operator with phrase 1. So this is mapped to positive operator with phrase between 0 and 1. So it actually defines map of state. And we also need complete positivity. So this is defined by this condition, but this just express compatibility with tensor product that is composition of quantum systems. Okay, so let V of H denotes the set of boundary operators. Then, so this is a fact from functional analysis theory. There is a one-to-one correspondence between bounded maps between the set of phrase class operators and fixed continuous map between the set of bounded operators. So this is basically because T of H is Banach space and its dual coincide with V of H. And mix the continuous map between V of the set of bounded operators called normal map. So so this correspondence restricts to quantum operations, and then the corresponding maps are normal, completely positive pre-unitary map. Pre-unitary is defined by this inequality, and it seems more common term is sub-unitary, but I accidentally adopt this pre-unitary. So anyway, so that quantum operations are in two equivalent forms. So then now T of H is a span of density operators. So this can be seen space of state Y. P of H is span of density operators. So this can be seen algebra of observables. So now we can understand that the top map is quantum operation in the Schrödinger here. And this bottom mark is quantum operation in Heisenberg feature. So, okay. Then, so we will review Selinger's work on QPL. So, Selinger proposed in 2004, 10 years ago, languages QPL and QFC, but I will not distinguish them. So I just say QPL. This is first of the functional quantum programming language with loop and recursion. And there are two data types, qubit and bit. And this is written as flowchart like this. So this is a very easy example. So how does it work? So first we have nothing here, and then here we allocate qubit initialized to be kept 0, and here apply atom aggregate, and here we measure this qubit. Then so there are two possible outcomes. So if we get 0, then the state is changed into this state, and this corresponds to kept 0 with probability 1/2. And in the other case, we get this state, and this corresponds to kept 1 with probability 1/2. So what's denotation of semantics for QPL? So we can expect an interpretation of this program will be given by quantum operation of this type. But actually it is unclear that how to give interpretations of these programs. So actually, Kraus simple quantum operation is not suitable for classical control or data. And Selinger's solution is to generalize quantum operations into map of this type. So now domain and codomain can be direct sum of the set of matrices. And this map, this linear map, is a quantum operation if it is completely positive and traceable equity. Then, so we can now give interpretation of this program as quantum operation of this type. So it is convenient to define category to consider denotation of semantics. So define category Q as its arrows are quantum operations we define now. Then it turns out this category is a symmetric monoidal category. So this monoidal product is given by Kenta product, and it has finite product. This is given by direct sum, and moreover, Kenta product distributes over finite direct sum. And moreover, this category is omega CP0 enriched symmetric monoidal category with omega CP0 enriched finite product. Here, omega CP0 is the category of pointed omega CP0 and omega continuous map. And omega CP0 enriched means each concept is pointed omega CP0 and composition is omega continuous. So then, essentially from this structure, Q gives semantics for QPL with interpretation types in this way. Here, of course, omega CP0 enrichment is used for interpreting loop and recursion. Okay, but here, what is important for my work is categories that have the same structure with Q also can give a semantics for Q pair. And so here we need some similar conditions. But anyway, this Q gives a semantics Q pair. So we now move on to operator algebras. So operator algebras is originally algebras of operators. That is star sub algebra of E of H. But we can also define them abstractly in Hilbert space free way. So C star algebra is abstract counterpart non-closed star sub algebra of B of H, and W star algebra is abstract counterpart of weakly closed unitary star sub algebra. And this is also known as von Neumann algebra. So historically, first, von Neumann algebras are introduced by von Neumann. This is motivated by quantum theory. In the context of quantum theory, operator algebras are seen as algebras of observables. And algebraic quantum theory refers to a quantum theory putting emphasis on operator algebras rather than Hilbert space. And this approach is actually has been successful in areas such as quantum field theory and quantum statistical mechanics. So actually there are several characterizations of W star algebras, and here is Sakai's one. So W star algebra is a C star algebra that has a trivial. So there exists Banach space. Its dual coincide with M. And in fact, we have already made one example. So T of H is trivial of B of H. So B of H is a W star algebra. And usually, map between W star algebra is required to be weak subcontinuous, and such a map is called normal map. And also we already know one example. So quantum operation in the Heisenberg picture is by definition normal completely positive pre-unitary map. So now let's define category W star CPPU as its objects are W star algebras and arrows are normal completely positive pre-unitary maps. Then quantum operation in the Heisenberg picture is an arrow in this category. And moreover, so by dualizing Selinger's quantum operation, we also get arrow in W star CPPU. And this correspondence is bijective, so this gives a full embedding from category Q to the opposite of W star CPPU. So we have seen two types of quantum operations, so Kraus one and Selinger's one. But now we can see both of them is generalized as normal completely positive pre-unitary map between W star algebras. So this category, W star CPPU, naturally arises as the category whose arrows are quantum operations in the Heisenberg picture. And my work shows this category is actually nice enough to give a semantics of Q pair. Okay, so what's nice mean? So recall that there is sufficient condition to give a semantics of Q pair. So our goal is now this category satisfies this condition. So we actually use opposite. So W star CPPU is symmetry monoidal category. This tensor monoidal product is given by a tensor product called spatial W star tensor product. And also it has a finite product. given by direct sum of W algebra. And one was tensor product distribute over direct sum. So now our main problem is whether or not this category is omega CPT or enriched. So, but the answer is yes. And in fact, we can say more from. So this category is actually DCPPO bottom enriched. Here, DCPPO bottom is the category of pointed DCPO and strict Scott continuous map. So, but how can we show that? Actually, every W star algebra possesses a property called monotone closedness. That is, every norm-bounded directed set of self-adjoint elements has a Schrödinger. So this is essential property of W algebra because this property gives another characterization of W algebra. So and you might notice this monotone closedness is similar to directed completeness in domain theory. And actually, there is a connection between them. So a C star algebra is monotone closed if and only if its unit interval, or it's also called the set of effects, is directed complex. So now we can see the unit interval of W algebra is always a DCPO. So, and normal maps has also characterization, domain theoretic characterization. So, positive pre-unit map between W algebra is normal if and only if its restriction to the set of effects is Scott continuous. So W algebra behave well domain theoretically. And this DCPO structure of W algebra gives to Hom set with this modeling, and we get the theorem. So every Hom set of W CPPU is a positive DCPO. And we can also show the composition of arrows is strict Scott continuous. So therefore, now we see W CPPU is DCPPO bottom and its category. And we can also show tensor product of maps and coupling of maps are strict Scott continuous. So now we get results that W CPPU is DCPPO bottom and its symmetric monodromy category is DCPPO bottom and its finite product. Okay, so good. Then, so now we see its opposite satisfies all conditions of following. So note that DCPPO bottom enrichment implies omega CPPO enrichment. And here we use opposite because here we need finite product. So this category gives a semantics of QPL. So let me make some comparison with Selinger's original semantics. So because that there is full embedding of Q into opposite of W CPPU. So this is contravariant because maps in Q are in the Schrödinger picture, while maps in W CPPU are in the Heisenberg picture. And it is easy to see this this factor through the category of finite dimensional Dualising algebras. And in fact, this factor is a part of equivalence of categories. So this category can be seen as an infinite dimensional extension of the category Q. And it is worth noting that the category of C-star algebras and completely positive free-unitary maps does not work because C-star, so this category is neither DCPP bottom range nor OSCPP range. So Dualising algebras are the appropriate set. But also note that in finite dimensional case, C-star algebra, there is no difference between C-star algebras and Dualising algebras. So using Dualising algebra, so it allows us to give an interpretation of infinite types. So for example, the bit is interpreted by direct sum of 2 C's, and street is 3 C's, and not a type of natural numbers is interpreted by direct sum of countable many C's. And this is actually Dualising algebra, but not in Q. Example 2. So Q bit is interpreted by M2, the set of 2 times 2 matrices. And Q trig is M3. And so then Q naught, I don't know if the Q naught is appropriate or not, but Q naught is interpreted by E of H. Here H is countable dimensional Hilbert space. And we cannot, so this Q naught cannot be interpreted in the category Q. So we can generalize first example. So notice that all of them is L infinity space of some set. And in fact, this gives everything of categories from the category sets to opposite of the category of commutative Dualising algebras. So it means classical computation in set, so it's deterministic computation, arises as a map between commutative Dualising algebras. So there are several future ones, and the most natural one is semantics by operator algebras for higher order languages or quantum number calculi. And so one reasonable question is whether or not this category is monoidal closed, and it seems it's difficult to problem. Another future work is to exploit the duality between commutative Dualising algebras and measurable space. So there is the Gelfand duality between commutative C-star algebras and compact partial space, and it seems there is a similar result for Dualising algebras, commutative Dualising algebras. And so this is to exploit this is potentially useful, for example, to study commutative classical computation in quantum setting. Okay, so this is a summary of this talk. And so I believe Dualising algebras give a flexible model for quantum computation. So for example, it accommodates naturally infinite dimensional structure and classical computation as a map between commutative algebras. But I'd rather say this work is only the first step, and there are a lot of things to do. For example, so this Venera is one of my colleagues. He also worked on W algebras, and his work is closely related to my work. So I regret that he is not here. So instead he will give a talk in MFS in the next week. So I guess some of you will hear his talk. Okay, so thank you for listening.
Thank you.
In sort of programming language semantics, infinite types often arise as solutions of domain equations. For example, lists are the initial algebra of some functor and so on. Can you solve domain equations in this category of
So this is the very what this is work is create this program. Actually, Matisse showed the category of W algebras and positive pre-unitary maps are algebraically compact for some class of functors, which allow us to obtain recursive types, something.
So you said you use the spatial tensor product on W star algebra. Can you say something about how that is being different from other tensor products? What is the spatial?
Yeah, but actually it is most natural tensor product for W algebra. And it coincides with tensor product of fundamental algebra, so it's very natural.
Does it coincide with tensor product of the underlying neighboring spaces in case of B of H?
Yeah, yes. So stars are algebras of B of H.
So the completely positive maps are somehow the correct ones into the dimension.
Yeah.
Any other questions, comments?
Can you elaborate more on the sister algebras and not the right model? So you said that sister algebras are not that complete structure.
So it don't have.
Can you be more intuition on this? So this is for the tensor.
Yeah. So one typical example, sister algebra, commutative sister algebra is continuous function from some compact Hausdorff space. And take so for example, consider to a sequence of functions, continuous functions, tends to like this, then it is not continuous function. So this is actually this gives a counterexample that for the category of C star algebras is not DCT oriented, not omega completeness. Yeah, and omega completeness is even greater.
So is it correct to say that C star algebras are sort of a non-commutative generalization of continuous functions and W star algebras of measurable functions?
Yeah.
And you want probability distributions and so on, so you need measurable.
More like Borel.
Oh,
Instead of look at measure.
Okay, thank you very much again.